Good afternoon, everyone. Today I'm going to present about evorobotgami, co-designing with humans in evolutionary robotics experiment. Let me briefly introduce what is evorobotgami. It is a combination of intuition and try and error that perform well in a range of environments into the initial population, where subsequent population of robots are optimized via a genetic algorithm and map elites. So what is evolutionary robotics? It is executed the same sequence of actions repeatedly. When it is applied well, the researcher doesn't need to make decisions about every detail of the robot design. In my cover solutions, the researcher did not thought of, especially for robots that are non-intuitive for a human to control or design. The motivation of this research is to improve an evolutionary process. This research paper combines the benefits of evolved and human design in a way that does not require the user to constantly interact with the design software to tweak designs, nor stop the evolutionary process to wait for the user input. Rather than tweaking computer designs, users iteratively tweak their own designs based on fitness and visual behavior feedback from the simulator. This research is important because it helps to eliminate dangerous jobs for humans, such as handling heavy loads, toxic substances, and repetitive tasks. This helps to prevent many accidents and also help to save time and money in the long term. This interactive evolutionary algorithm is used in this research paper. The objective of this algorithm is to integrate human input into evolutionary algorithm. For example, expert knowledge can be used to set parameter limits and to design fitness function. The user receives on their choices is at the end of the experiment when solutions can be analyzed to see if these settings produce the intended result the user wants. This is the second algorithm used in this article. The objective of this algorithm is to produce a wide range of high-quality design, such as generating valuable feedback to the user, and with two popular variants, NSLC using parental optimization to maintain diversity, and map elites which use a discretized feature map. This is Robotgami Designer. It allows the user to create independently manufacturable robot parts together. It also provides interactive feedback to users, guiding their exploration by checking validity and manufacturability of the design at each step. The first step is to integrate Robotgami Designer to the system loop. We simplify the user interface and add design constraints to the software to limit the design space. The second step is to link the software to a simulator that evaluates the design fitness and provide user with visual feedback. The third step is develop a compiler that compiles the user design to design vector that can be loaded by the map elites searcher. The fourth step is wrap the software with a user study guiding system that helps the users go through the user study with minimum interruption by the researcher. Robot morphology and gaits. Evolutionary robotics use a range of robot representation which can be classified as direct or indirect. We use a direct representation that captures these features to balance the genome complexity and design space expressiveness for aiding human design exploration. In this research paper, we consider leg robots with 2 to 6 legs. Each of it has 2 to 3 links. The genome shown in picture A, allele ranges shown in B, and mapping to a phenotype robot is shown in picture C. Slide, the legs are divided into 2 groups. Starting from the front left leg, Alternating group numbers are assigned in clockwise order, so group 1 executes the motion sequence M1 to M3 simultaneously as group 2 executes M2 to M1, and the process repeats over multiple gate cycles. The group switches to the next joint target when all the joint angles are within 0.01 radian of target angles, or 3 seconds after the other group finishes its current motion, whichever happens earlier. The gate is controlled by a pi controller over both velocity kp equal to 10, ki equal to 0.3, and the position kp equal to 2 and ki equal to 0, with a maximum joint velocity of 2 radian per second. This was used to remove a potential level of indirection and predictable control output per morphology. Moving on to the next slide, task and fitness. To make sure the participants of the user story could get some good intuition on some problems, they defined the task for the robot to be simply walking forward in different environments, which is ground, side, valley, with increasing degrees of difficulty of walking forward, and define the fitness to be heavily determined by the distance traveled during the given time. And they use Project Chrono as the simulator. So at the start of each simulation, the robot is placed at a fixed point at one end of environment with Z position determined by having the foot of its longest leg lift above the terrain surface directly under it by 2 cm. The robot is then simulated forward for 30 seconds of simulated time with simulation step size of 0.05 seconds. Ground is the easiest task and side is a bit difficult as it got the bumps, and valley is the most difficult due to asymmetry which counter to most human designer intuition. The fitness objective F from equation 1 is to maximize the distance of robot moving forward while minimizing divergence from a straight line. Moving on to the next slide, Map Elite Searcher. It links the simulator for fitness and feature evaluation. It also hosts population in the archive map, which is discretized low-dimensional projective space of search space. It used a 2D map of 20 × 20 cells with two-dimensional features. The first feature is the length of body along the x direction, and the second feature is the standard deviation of leg lengths. These two features were chosen through a small number of test runs using random initial population. And these are the settings. I will not talk much on this. Moving on to the next slide, experiment testing. So to explore RQ1 and RQ2, we set up 5 test conditions with varying numbers of human and random design. Each HX is repeated 10 times with random design uniformly resampled for each repeat. Moving on to the next slide, which is the result. In conclusion, results demonstrate that when humans have a reasonable understanding of the problem to be solved, their inputs have beneficial effects on subsequent evolutionary process, yielding higher base fitness and higher mean archive fitness. So a mixture of human and random design, HR5, achieved good results in all metrics for ground and side, where the human intuition is reasonable, suggesting an optimal balance of two sources of design. At last, I will talk about the dislike and like about this research paper. I like the process where they implement it with injecting human suggestion into the robots, and the evolutionary algorithm does the tweaking. This helped the researcher to complete what they wanted, and the robot can try to learn what the researcher wants, and the researchers can look at the visual feedback and keep changing until they're satisfied. And the dislike about this paper is taking too long to run for one run, as it requires 6 hours. So we might need many computers to run more effective results if the human suggestions are wrong, and we might need to run another 6 hours again. which is really time consuming. Thank you.